It's cartoon time. This is how chapter 8 is going to go. I'm not going to follow step by step what's in the book because they don't title it difference equations. They call it discrete dynamical systems, which is the same thing. Difference equations are a type of discrete dynamical system. And I'd like to focus on difference equations first. It's mentioned in the first section of the last chapter, and it's going to be a good way to see how this chapter fits in to the rest of the book, because it looks like we go from doing things that required Calc 1, 2, and 3 and all sorts of new ideas, and all of a sudden we're in this other world where we don't use any of those old ideas, but we actually do. So I want to focus on difference equations so you can see the connections. So here's the story. My variable is n, and it stands for time, just like it did back in the other previous chapters. But n goes from 1 to 2 to 3 to 4 to 5. So there's a time step. We don't have a continuous time axis. And the variable is also not continuous, because the dependent variable, we're going to call it r sub n. It stands for the number of red turtles. Now in this cartoon here, I've got 50 red turtles. 62% of the screen is blue. And the program says if a red turtle lands on blue, it's going to turn green. So you can see like this little red turtle right there. He's on blue. As soon as the program starts, he turns green. And all the turtles march around at random. Now, if a green turtle lands on yellow, it turns back to red. But you can see only 12% of the screen is yellow. So what do you think is going to happen, Bruce? And Bruce says, oh, we're going to have a big drop off in the number of red turtles right away, because look how much the screen is blue. And Bruce is right. What else do you think is going to happen in the long term? Are the red numbers going to fluctuate way up and down? Or are they going to stay low? And Brienne says, I think the red turtles are going to stay low because there's just not very many opportunity to make more red turtles, except for when a green turtle lands on yellow. And that's a good observation. So let's see what happens when we tell these turtles to do their thing. And oh yeah, immediately a ton of red turtles turned green. And once in a while you see a new red turtle being born. But yeah, the number of green turtles stays high and the number of red turtles stays low. Let's see what that looks like in a graph. So here's the graph of what went on there. And you can see here's 5. The number of red turtles actually went below 5 for a minute. They stay below 10, except for here. They went above 10 for a second. So there's this huge drop off when you have 50 red turtles and you go down to 5 red turtles, at time step 2. Boom, But the number of red turtles is sticking around in a steady state somewhere. It looks like, do you think the steady state's 10? I think it's below 10. Do you see? Okay, we can do this all day. Let's just do one more to see if we get a similar spread, because there was some randomness here. I'm going to create I'm creating 50 red turtles. Oh, I got to kill everybody. The old turtles are still there. Create 50 turtles so I only have 50. I'm going to make them run around for a while so they're all spread out. And now I'm going to kill the old plot because I don't care about the old stuff. You can see where I made 50 more red turtles. So at this point I had 100 turtles. Let's stick with 50 turtles. That's just me. All right, so here we go. I've got 50 turtles, and we're going to make them run around, and I bet, we get a huge number of them turning green again right away, and we do. Bunch of green turtles appear at time step 1. And then the number of green turtles goes way up to the 40s, it looks like, and then just stays up there. And the red turtles stay down close to the single digits all the time. So let's take a look at our plot. And the plot, yeah. Let's get the whole thing on there. So this line is 10. And I got to get above 10 a little bit more than usual, but it's coming back down. It's probably going to, stay somewhere in the low 10s because I got below 5 here, and here I'm at 6. So yeah, so what's the math behind this stuff? That's what we're going to see next. This is the math of difference equations, everybody. You got to say what your variable is. So r sub n is going to be the number of red turtles at time step n. Our answer, we seek a solution, and it's a function. It's going to be a function of n. Little n is the time step. So it's not different from what we did before. The horizontal axis is still time. But the time only happens at time equals 0, time equals 1, time equals 2, and we get little numbers for them. So here's what happens. We're going to model what happened on that screen, that cartoon that we saw. 62% of the red turtles change color. So the old red, think of this as old red, 1 minus 0.62 of them stay red. So I don't use 0.62 times that because that would be counting green turtles. So here's the old red turtles, new red turtles. Now where else do we get new red turtles from? It's either old red who stayed red or green turtles, that's not 0.5, that's 50. Green turtles, that's 50 minus the number of red turtles. And it's 0.12 of those turn red. So new red is old red who stayed red plus green who turned red. So multiply through and simplify and everything. And here's the guy we care about right there. This is our difference equation in simplified form. And now you say, how do you solve something like this? Oh, it's easy. You guys, it's what we've been doing. Here's the connection to the rest of the semester. You do the homogeneous case first. Pretend that this term that doesn't have n and doesn't have r on it, pretend it's 0. So that leaves us with r sub n plus 1 equals 0.26 times r sub n. This is like having y prime equals 0.26 times y. Only now it's just time steps. So here's your change in time, 1 step. And now look, we need something that works like this. If you multiply by 0.26 each time, it's literally saying it because this is your time counter, n plus 1. Each time you multiply by 0.26. Oh, well that's 0.26 to the n. But it could be times a constant. The arbitrary constant in front for the homogeneous solution. The homogeneous solution gets the arbitrary constant. And it's order 1 because it's n plus 1 and n. So it's order 1. So I only get 1 arbitrary constant. And now over here, the particular solution, here's where the 6 comes back in. But our particular solution is we're looking for the equilibrium. And that's why it's an E. The book uses E, other books use E, I'm going to use E. E is the equilibrium, which says where is the number that we hit with 0.26 and add 6 and we get the same number back. And that number is 8.12. We solve for that. Now what does that mean? Well, what do you do? What do you do? What do you do? This one's for Owen. Owen, what do you do with the homogeneous solution and the particular solution? And Owen says, oh, you just add the particular solution to the homogeneous solution, use the initial conditions to take care of the arbitrary constant, and you should have the specific solution. And that, you guys, that's the thing. Haven't you got that down? You don't need notes to do that, even though, yeah, it's open book, open notes and everything, but you've got this dance down. If you don't have this dance down, you should be embarrassed because that dance, we've been doing it for a long time now. All right, so I now have the difference equation, the initial condition. I'm going to take the initial condition, n equals 0, r is 50. So I have 50 equals a times 0.26 to the 0, which is 1, plus 8.12. So I don't need this anymore. I've got that written down. A homogeneous solution plus the equilibrium gives me the general solution, but I'm looking for that arbitrary constant. So the nasty part goes to 1. How many times have we seen that? So I have a equals 50 minus 8.12. So that gives me my r sub n is equal to 50 minus 8.12 is 41.88. And that's times the 0.26 to the n plus 8.12. So let's check this out. Here's something we didn't do at the beginning, but we could have done. Take this equation and put in r sub 0 is 50. And the next thing we get would be the next number. So the book is going to ask you to do that. I might ask you to do that. So you put in 50 here, 50 times 0.26 plus 6. Take that number, put it in here, times 0.26, add 6. Take that number, put it in here, times 0.26, add 6. You will get the thing called the time series. Let me show you what I was talking about there. So for n, this is fitting, good, and r sub n, 0, 50, 1. And you have to do on your calculator, which I'm about to do, 0.26 times 50 plus 6. And I get 16. Wow, the number of red turtles went from 50 to 16. Looks like the cartoon. Time step 2. I take the 16 times 0.26. Add the 6. And I get 10.16. Wow, we're already getting down very close to the equilibrium of 8.12, and it's only 2 time steps. Now let's do this problem. I would like to do 41.88 times 0.26 to the second. I'm going to do n equals 2. I'm just showing you that I should get exactly the same thing. And I get 10.95 for that. What did I type in wrong? I should have gotten exactly the same thing. All right, well, I'm going to deal with that later because this video is going pretty good. I should have gotten the exact same number. Maybe you guys can spot if I made an algebra error somewhere. But I should get the same series here as I get here. I should get the same stuff. And then, let's say you graph it. Let's say you graph. So you get the y equals. Let me see if we can get that on the screen there. There it is. So that's my equation, and I got a graph. And it's not lumpy looking like the star logo graph, but it gets down to that horizontal asymptote really quickly. All right, I'm going to look for my little math mistake and maybe make a note in the video thing. This thing should generate the same time series as this. So I'm on it. Maybe it's a round off, something like that. All right, see you later.